Good evening. My name is Elri Winnett-Seelig. I'm a fellow of the Linnean Society, and I want to welcome you and, of course, Fredi for the discussion this evening. So one of the things that we like to do at the start of these sessions is really to understand who's in the audience. It helps Fredi and our speakers really understand sort of what people are like, why they're here and who they are. But it also helps us understand how we're getting into the community, which is one of the primary objectives that we have right now in terms of the Linnean Society. So one of the things that we ask is, how many of you in the audience are members or fellows of the Linnean Society? Oh, great. Look at all the people who aren't raising their hands, because that's a great target market. One of the things that's so special about the Linnean Society, and you can look around at the members and the previous presidents of the Linnean Society, it's a very broad church. So the Linnean Society is the world's oldest learned society for the science of the natural world. It was established in 1788, and really besides Carl Linnaeus, what we're really known for is the work that was presented in terms of Alfred Russel Wallace and Charles Darwin and the theory of evolution through natural selection. I confess that I actually only found out tonight that it wasn't in this building on this podium. It was actually next door. But the reality is there's such a deep, rich history, and it's people made up of scientists, artists, amateur naturalists. And so it's a very broad church, and we really would love to chat with you about your interest in joining the work that the Linnean Society does as a not-for-profit. So we're having drinks upstairs after Fredi finishes. So we'd love to chat with you about whether or not you're interested in joining as a member of the Linnean Society. So that's my plug. And now actually you are here to talk or to listen to Fredi. So may I introduce you to Dr. Fredi Otto. So Fredi is a professor of climate science at Imperial College. And she also is a co-founder of something that's very interesting to me in terms of, she's a co-founder of something called World Weather Attribution, World Weather Watch. And it's really looking at the attribution, sorry. What it does, the work that she's doing is so important because it actually starts looking and dimensioning how climate is actually impacting the likelihood and the severity of extreme weather events. And that's work that's really progressing too slowly for us to be able to action it. So with that, I think what's really important is Fredi has deep scientific credentials. She's a climatologist, but she's really widened the aperture to really examine what are the drivers of climate-related change and how can we actually address them in a holistic manner. And with that, may I introduce you to Fredi? And Fredi, would you like to take the floor?
Yeah, thank you very much. And yeah, thank you for having me here. I feel I really don't know enough about biology to be allowed to stand here, but I do know about the climate system. And although I'm actually not a climatologist, I'm a physicist by training, and then did a PhD in philosophy, but I've been working on extreme weather events and climate science since that. And so what I'm doing today, because it's sort of a science society, is to talk a bit about the science of how we know that climate change is affecting extreme weather events, and then why that matters. So, first of all, to get a bit of the sort of the bigger picture, when we talk about climate change, and when we talk about climate change, particularly outside of the scientific community, and then about climate policy, we always talk about something like global mean temperatures, like reaching 1.5 degrees of global mean temperature or reaching 2 degrees, as if, and this is why I have a screenshot here of a video from a friend of mine who is a YouTuber and who does videos explaining climate change, as if it's a bomb that will explode when we reach 1.5 degrees, or as in maybe some of you have seen the movie Don't Look Up, as if there's an asteroid falling on Earth when we reach these temperatures. But that's really not how climate change manifests. Climate change manifests through changing sea levels, rising sea levels, melting glaciers, but most fastly through the changing intensity and likelihood of extreme weather events. And when we talk about extreme weather events, we usually illustrate them with pictures like this. And these are from our website, World Weather Attribution. So we are as guilty as anyone else about that. But these extreme weather events, we care about them, and we care about climate change because they affect people, they disrupt lives and livelihoods and affect economies. And so they cause what we sort of in a climate science, climate policy term call loss and damage. And we've long been in the era of loss and damage. It's not something happening in the future, it's happening today, and it has been happening for decades, but with every ton of carbon that we burn, of course, these effects get stronger. And so this is, as I already just said, so this is the kind of research that I'm doing with my team, and this is my current team. And I founded World Weather Attribution 10 years ago, together with this man, Fredi Otto van Oldenburg, but he passed away in 2021. And the aim of our research is to provide scientific evidence of the role of climate change in the immediate aftermath of an extreme weather event occurring. So we do science, just very normal science, as you also do in the sort of peer-reviewed literature, but we make our results available before peer review, so in the immediate days, weeks, and months, depending on the type of event occurring. And what you can also see here is I show the media mentions of our studies since 2020, and you can see, well, there is definitely an increase, so people do want to know more about the role of climate change. There are also very distinct peaks that you can see. And the biggest one that is on there was an extreme heat wave that hit the US and Europe almost simultaneously. So basically all the big international media was talking about nothing but heat. And the other big spike there, that's Hurricane Helene that hit Florida and the Southern Appalachians in the US later in September last year. And I will talk about these two types of events that are actually the ones that we know most about, because in the US and in Europe and the US and Europe, we have most data. So we have much more information than in other parts of the world. But of course, that doesn't mean that these events don't happen elsewhere. It's just there's a lot less attention. And there's often a lot less data to actually know what helps. But as I said, heat waves are happening all over the world, and they are the type of extreme event that increase most strongly with climate change. And so these are, if you're interested in this, you can have a look at our website, because they are all on there. So these are just some studies on extreme heat that we did in recent years. And you can see, for example, extraordinary March heat wave is 10 degrees hotter than it would have been without climate change. And this one, extreme heat killing more than 100 people in Mexico, was also one of the big spikes where people really paid attention. Paying attention in the moment, unfortunately, doesn't necessarily mean paying attention enough to actually prepare for the impacts of heat. And so what I will do now is I will use this heat wave that you can see the headline of the study, which is not very snappy. Extreme poverty renders Madagascar highly vulnerable to underreported extreme heat that would not have occurred without human-induced climate change, just to explain what it is that we are doing and how we know. And then I will talk about two other events that are probably much more familiar, to talk about why it also matters to us and not just to Madagascars. So, but to start with this event that happened in October 2023. And the very first thing that we have to do in every attribution study is to characterize the event. So to find out what has actually happened. And that sounds very straightforward. And in the UK, that is very straightforward because the UK Met Office has a definition of what heat wave is and has that for different regions. So here in the southeast, it is 3 days or more above 28 degrees. In Scotland, it's 3 days or more above 25 degrees. But almost all other countries in the world do not have any monitoring of extreme heat or any heat wave definitions. And so there are no early warnings. And also it is, we have to actually look at observational data to find out what happened and how do we characterize the event. And what you can see here on the left-hand side of the slide is Madagascar, and it's the 7 hottest days during that month and the anomaly in temperature. And you can see that particularly in the mountainous region, which is on the eastern side, where you also have the capital, Antananarivo, the temperatures were particularly high. But actually in that month, the whole month of October was extremely hot compared to usual Octobers and compared to any other temperatures across the whole year. So we used a very simple way, one very simple way of characterizing this event, and that's just average October temperatures over the whole island of Madagascar. And this is also why I use this as an example, because it's a very simple definition. And then this is often, and this might be surprising, but this is often actually the hardest part in all these attribution studies, is to find out what has happened, how much that has happened has to do with the impacts that we care about, and to find good data to identify what has happened. But when we've done that, so now in this case, we have done the first step, we have characterized the event. So it's October temperatures in the year 2003 as they happened in that year. And the next step is then to find out what kind of event is that in the world we live in today. So compared to all possible October temperature events, what is it a 1 in 10 year event? Is it a 1 in 100 year event? So is it a really rare event or it's a fairly normal event? And to do that, we use weather observations, statistical models, but also climate models. So the same models that I used just also for weather forecast, and simulate with these models all possible weather events, so all possible October temperatures that can occur in the world we live in today with the 1.2 degrees of global warming that we had at the time. And the result of that is what you can see here in these red curve. So that's just the probability distribution of possible October temperatures. And you can see that sort of the average October temperatures in the world we live in today are somewhat around 24 degrees. But the event that we have observed, which is just about 25 degrees, is actually quite a rare event. So even in today's world, it's about a 1 in 100 year event. That doesn't mean it happens every 100 years. That just means in any given October, there's a 1% chance in our current climate of such an event to happen. And that's what is sort of illustrated here in this graphic in the top row in the middle, with this one pink dot in a sea of gray dots. That's sort of the likelihood of the event. And then once we've done that, we do the actual attribution step. And the actual attribution step is finding out what's the role of climate change. And because we know very well how many greenhouse gases have been put into the atmosphere since the beginning of the Industrial Revolution, we can take them out of the atmosphere of our weather models and climate models and simulate the world that might have been without climate change. And we can also use statistical models and simulate how would our observations have looked like if they had happened in a world that has globally 1.2 degree less in terms of temperatures. And you can see the result of one of these model simulations. We usually use as many models as we can get our hands on, but you can see the result of one of them here in this graph, and this is the blue curve. And what you can see here, in the world that would have been without climate change, the average temperatures of October temperatures would have been a bit below 23 degrees for October in Madagascar. And you can also see that actually the event that has occurred would never have occurred if it wasn't for climate change, because in this world of possible weather without climate change, we never get to temperatures as high. And so this is what's then illustrated here in our summary graphic. Without climate change, we would never have had this event. So this is one way of looking at an extreme event. You can say we use the magnitude of the event and look how has the likelihood of it occurring changed. But we can also say, okay, the 1 in 100-year event today is 25 degrees. How cold or how hot would the 1 in 100-year event be without human-induced climate change? And we can get that information from exactly the same simulations that we've used. And this is what is illustrated here. So this is today's event with the 25 degrees October temperatures, and it would have been about 1.5 degrees cooler without human-induced climate change. So that's two ways of looking at the same kind of information. You can either look at how has the magnitude changed, the severity, or how has the likelihood changed. And then the last thing that we also always do is, of course, we can use the same models to look into, okay, how would this change if we keep on burning fossil fuels, if the world gets warmer? And so this is what you can see here in the last column of this illustration. If we had 2 degrees of global warming, this event would not be a 1 in 100-year event, but it would be roughly a 1 in 5-year event. So in any given year, you had a 20% chance of such an event occurring. And similarly, you also have temperatures of close to 26 degrees. The difference of 1.5 degrees in October mean temperatures might not sound very much, but I will illustrate very soon that that actually makes a huge difference. And there are a huge number of ways of how heat, and even what you might think is moderate heat. But if we had an average temperature of 25 degrees in London for a month, it would be unbearably hot here. And the heat wave affects human health, but it also affects agriculture, and that will have been one of the key problems in Madagascar, because a lot of the country depends on agriculture and also on only on agriculture. So a lot of people don't have any other means of income. It particularly affects water availability, because when you have high temperatures, water evaporates faster, so you have low water levels in rivers. The water gets very hot. That also means you have a lot of waterborne diseases than you would have otherwise had. And working outdoors, so people working outdoors are extremely affected. So in a very poor country like Madagascar, it really disrupts the whole way of life, because if you have your economy disrupted, you have your water supply disrupted, you have much less access to medicine, and people already live in poor living conditions. And therefore, such a heat wave might not actually be reported as anything special, but it has huge impact, and it's something that we severely underestimate. But we also have heat waves in other places of the world, for example, here in London, and where we have a lot more data to not only give a broad overview of what the impacts are in a sort of busy diagram like this, taken together from research from all over the world, but where we can actually calculate what these kind of changes in extreme heat, or also what doesn't always sound like extreme heat, mean. And so this is a study that we did last week together with a group of scientists from also here in London, from the Institute of Tropical Medicine and Hygiene, where we looked at, okay, what does a 2 to 4 degree hotter heat wave in Europe actually mean in terms of the effects on mortality? Because that's one of the key impacts of heat wave, is that they are killers. And they are called silent killers because people don't usually drop dead in the street, but they die often alone in their poorly insulated homes. So here we have taken 12 cities, and there's nothing particularly special about these 12 cities. It's 12 cities for which we had data that are distributed across Europe and that experienced a heat wave in the last days of June, sort of first days of July this year. And I didn't give you the whole 12 on this slide because then it would have been unreadable, but you can see here, so for London over, and we sort of defined the heat wave as the 5 hottest day in this 10-day period that we looked at. And for London, the event was about 24.5 degrees. In Milan, it was 30, Barcelona also 30, Madrid similar, Lisbon a bit cooler. And then what you have in the next column is the return period. So as I said with Madagascar, we found it was about a 1 in 100-year event, so already still relatively rare today. But we found that these kind of heat waves that we've all just experienced are not very rare. So in London, it's about a 1 in 6-year event in today's climate. In Milan, it's even one that is basically an annual occurrence now. In Barcelona, a bit more rare. And the only exception that we had, and the others that are not there have all very similar to sort of between 2 and 6. The only exception is Lisbon, where it was actually an exceptionally hot event. So, and then on the very last column, you find what we found out. So we have then, you said, okay, this 1 in 6-year event, London heat wave, how different would the temperature have been if it was a 1 in 6-year event in the world without climate change? And we found it would have been about 4 degrees cooler. So you can see lots of the uncertainty around there. So between 3 and 5 degrees. And again, Lisbon is the exception here, where it was only about 1 degree cooler than it would have been. And the reason why Lisbon behaves so differently than all the rest of Europe is because land warms much faster than the ocean, and Lisbon is very much part of the Atlantic in the data that we can use. So what we've then done, and this is work from the epidemiologists at the London School of Tropical Medicine and Hygiene. So they have done through very dedicated work over years, developed these temperature mortality curves for different age groups in different cities and for different parts of the population in actually 850 European cities. And they have said they would like us to do it for 850 cities. And we've said, no, sorry, we can't deal with 850 cities within a week. Let's take 12 and then do the rest later. But so what they have developed are these curves that you can see here on the left-hand side. And they show you the temperature percentile. So 50% is sort of the average temperature throughout the year in a particular place. And then when you go towards the 99th percentile, you go to high temperatures. And when you go to 0, you go to very, very cold temperatures. And you can see that people are sort of most alive is close to the 50% and a bit above, and that there's an effect on mortality in cold temperatures, where sort of relatively slowly increasing towards cooler temperatures. But, and that's what we are going to focus on, is there's a very sharp increase to high mortality, or to above average mortality towards higher temperatures. And you can also see the different colors are for different age groups. So the older you are, the more vulnerable you are to extreme heat. And what's on the map here is what's called the minimum mortality temperature. And that is actually, I always find that surprisingly low, because when you look, for example, in Scotland here, it's below 17, between 16 and 17 degrees Celsius. So at these temperatures, people actually, when you have that as sustained over several days, people actually start to have an increase in mortality. But of course, that's when it starts. The curve really dramatically goes up very steeply, as you can see there. And you can also see that around the Mediterranean, that minimum mortality temperature is 10 degrees higher, because a lot, apart from age, what determines how susceptible we are to die in heat depends on the rest of the demographic structure. So if people have pre-existing medical conditions, they're more susceptible, but a lot is also depending on infrastructure. So what houses do we live in? Are they ventilated? Do they get hot? And does the heat stay there? And also behavior. So in more Mediterranean regions, the working day is structured much more around working in the early morning and late in the evening, but not during the day, which is very different to the northern parts of Europe. So, and now we've done the attribution, where we combine these two things. And you can see in these graphs in purple, the excess mortality. So how many people would have died in these 10 days of heat in that particular city in a world without climate change. And then in orange, how many are actually estimated to have died in the world we live in today. And you can see some differences. For example, in Lisbon, there is not much difference. And that's, on the one hand, it was if you remember, it was a very extreme event. It was a super rare event, even in today's climate. And so it would have already been quite hot without climate change for such a rare event, and the difference isn't so big. But in other places, for example, in Madrid, you can see that almost all the deaths are attributable to climate change, because without climate change, this minimum mortality temperature would actually not have been reached. And so, yeah, this is really just the summary figure for all 12 cities that we looked at. And on average, 2/3 of the death across these 12 cities would not have occurred if it wasn't for climate change. So if anyone asks you, tells you again, 2 degrees hotter doesn't really matter, well, they tell you basically they don't care about these people. Okay, so before I'll finish with heat waves, and I am talking a lot about heat, but it's also big. It's first of all where we have a huge climate change signal, and it's something that is still extremely underestimated. So I have shown you for the events that we looked at that we usually look at what's the event today. So and compare it to a world without climate change. But of course, we can also use the same methodologies and look at, okay, the world without climate change, beginning of the Industrial Revolution, that seems all very, very far away. But actually, climate change in terms of the big part of it is actually not so far away. So what you can see here is it's for a heat wave that we looked at in the US and Mexico. And we defined it as the 5 hottest days. And that was in the world we live in today, about 35 degrees. And the same event would have only been 33.5 degrees without climate change. But we also looked at how the difference was at the beginning of the 10th century, so just 25 years ago. And it would have been a lot cooler at the time. And that is, of course, because we're not only keeping burning fossil fuels, but we have actually increased the rate year after year after year. And so even if you're only 30 years old, the half of all the emissions have been emitted in your lifetime. And so that might sound very not optimistic, very pessimistic, that actually it's not been a very long time ago since we could have, if we had stopped then, things would be very different. But it also means, of course, that we have a lot of, that things can change very quickly and in a short time frame. And the really good thing about heat waves, and that's one of the most important things that was confirmed in the last IPCC report, so the Intergovernmental Panel on Climate Change, and that was mostly ignored, is that for things like extreme weather, like extreme heat, like heavy rainfall, when we stop burning fossil fuels, these things will stop getting worse. And that is good news, because it means we have agency. It's not too late. It's not already all down the drain. So very briefly, I want to talk about things that are not heat waves, because there are a lot of other kind of extreme weather events that are happening. They are, from a scientific point of view, a bit more complex to look at. So if I would go into detail, that would take a long time. So I won't do that. But this is just the events that me and my team have looked at in last year and this year. And you can see it's droughts, it's heavy rainfall, it's hurricanes, wildfires, and heat waves. And all the pink dots are events that have become more severe and more likely because of climate change. And there are a lot of pink dots. But there are also events where climate change has the opposite effect. And so you can see two of these green dots. One of them is not surprising at all. It's a cold wave in Europe. But the other one is a drought in Zimbabwe, Zambia, and Mozambique that happened last year. So where actually it would have been even more severe if it wasn't for climate change. And then there are a few events that you probably can't see that are white, where climate change don't really play a role. And then there are two events on here, and I would need to add another yellow dot because of a study we did today, where we had inconclusive results. And that means we just, from the data we have, we just can't find out what actually has happened, or we don't have climate models that are able to simulate these events. So, and as I said, I'm not going to go into detail here. If you have questions about that, you can ask me afterwards. But to do an attribution study on a hurricane, we would, in theory, do the same thing that we also do for a heat wave. We look at how to characterize the event, how is the likelihood in today's world, in today's possible hurricanes, and compare that with how would it be in a world without climate change. But characterizing a hurricane is more complicated than a heat wave. We can't just use temperature, because hurricanes are, well, the two things that really lead to damages are heavy rainfall and wind speed. But what actually provides the conditions for a hurricane or other kind of tropical cyclone to develop is called potential intensity. And that's a combination of the sea surface temperatures and the stability of the atmosphere. And that means if the atmosphere is stable, so if you don't have vertical winds, then a hurricane, if it has developed, can sustain. And if you have high temperatures, it can get more and more energy, and it will survive and become very destructive. And for heat waves, we also, without ever having done a study, we have physics. We know a warmer atmosphere will overall will mean that on average we see more heat waves and fewer cold waves. So and we do the studies to find out how does that exactly pan out in terms of temperatures. But for hurricanes, we don't really have that theory, because yes, sea surface temperature increase. That means we have more energy for hurricanes to develop, but whether we have more or less stability in the atmosphere is not something that comes neatly out of a theory. So we can't say a priori we'll have more hurricanes or fewer hurricanes. And so that's where we actually have to do the studies. And I mean, you can see the results here. I'm not going to talk about in detail how we came to them. As I said, you can ask me about it afterwards. So, but one thing I want to highlight is that we found that the wind speed has increased by about six meters per second. So, which is 13 miles per hour, which again, doesn't sound terribly much, but it actually means the difference between a category 3 and a category 4 hurricane. And then we, or not we, this actually didn't involve me or my team, but another team at Imperial College, looked at, okay, how does these 11% increase in wind speed, how does that translate? What did that actually do to the damages? And in this case, just the economic damages. And they found that 11% increase in wind speed means about 44% increase in the economic damages. And so that means that a hurricane that had an insured loss about 20 billion would have actually been 8.5 billion cheaper if it wasn't for climate change. But, and this will bring me to the end, because I promised to talk about justice and injustice. Of course, the insured losses are the thing that are relatively easy to deal with because you have insurance. It's the one thing where we have good data, so we can do studies like this, but it is not really why hurricanes matter, and particularly not for whom they matter, because the people that have no insurance are the ones who really suffer from these kind of events. And the hurricane hit, this Hurricane Helene hit in two slightly different regions. So one of them is down here is Florida, which is often hit by hurricanes, is used to hurricanes, where the death toll was relatively minor. I mean, every life lost is a life too much, but there was a very high death toll in the second region where the wind speeds and rainfall was very high. That is highlighted here. That's the southern Appalachian, which is not a region that is used to hurricane force wind speeds. They used a lot of rainfall, but not to that. And so that's one of the examples where we've seen a really high death toll. And one of the reasons is that when we do see that is sometimes when there is no early warning. So in this case, there was early warning, but a lot of people actually didn't know what to do with the warning, or they were told to evacuate. They had no idea where to, or how, or what time frame, and what that meant. And then, and that was also, or even though it was before Trump got into power for the second time, a lot of people in that region have a lot of distrust in the emergency, in FEMA, in the emergency disaster management. And so even if they were told you have to evacuate, your life's in danger, they thought that was a vogue idea. And so that is something that we've also seen with subsequent events since then, and increasingly in the US in particular, but not just in the US. So if you don't have trust in your authorities. And then I already said that when people don't have nowhere to go, but what's also a big problem, and that will also play the role here, is when something happens that's outside of what people, or at least the community, has experienced. Because here we have hurricane force winds, which is just something they are not used to. And we've seen the same thing a bit later in the year with floods in Valencia, which you probably also still remember, where there was a very high death toll. And one of the problems was that the local authorities didn't actually issue evacuation warnings, because no one thought that rain could be that bad, that it could rain that much in such a short time. And this is something where even small changes, because of climate change, especially in these where we see the strongest impact on rainfall is in the hourly rainfall. So a lot of rain in a very short time frame, which leads to flash floods and which gives you no time to evacuate. So that's why where climate change also plays a big role in when we see high death tolls. And so what really causes the damages is, of course, that there has to be a weather event. Well, what turns a weather event into a disaster is only very little dependent on the nature of the event, but very much dependent on all the other factors that I mentioned. And here it's just on the factors determining impacts of extreme events on individuals. You could make this list much longer and increase it to what impacts on agriculture and so on. And so in our studies, we always try and systematically also look at these factors. This means these factors are really what makes the difference between a disaster and severe weather. And this is just one example for a storm. It was the same storm happening in 23 over the Mediterranean that hit Greece and Libya. And in Greece, 17 people were killed, but in Libya, war-torn Libya with no early warning systems, with no very ill-maintained infrastructure, more than 4,000 people lost their life. And so without, this is sort of brings me to the end. And on the one hand, this is why climate change is so bad and why we care about it. And every time I tell these to my students, they are totally surprised. The Paris Agreement, so the global treaty that we have to limit climate change of ideally 1.5 degrees, is a human rights treaty, because climate change massively violates the human rights of the vast majority of the population of this planet to the benefits of a very small, rich, loud minority. And that is why we care about climate change in the first place. But it also means, of course, we have to stop burning fossil fuels to avoid these things from getting worse. But all these dimensions of vulnerability is something that will not change if we stop burning fossil fuels. It's something that we have to address as well, and that we have to address now. But it's also something that we can address much more easily. It is not something where you need an international treaty. It is something where you can, where a lot of things can be done on city scales, or at least on national scales, and where most of us have a lot of agency to actually shape what's happening. And so, we should use that agency. Thank you.